Question number 3. This time we've got a 330 millivolt voltage source, a 39 ohm resistor and a 33 nanofarad capacitor. We're being asked how much active power is supplied. Well, no active power is supplied to the capacitor. That just takes reactive power. No energy leaves a circuit in an ideal capacitor. So we're only interested in the resistor here. So this is really quite a simple problem. We take the 330 millivolts of voltage and the 39 ohm resistor, and we don't have to worry about the capacitor because it doesn't contribute to the active power at all. I can just do this one by taking 330 millivolts, that's my voltage, square it, divide by 2 because I'm using 0 to peak phasors, and divide by 39, and that would be my active power. It's really just the expression that we have from DC, power equals V squared over R, except we're having to put in that value of 2 because the voltage is not a constant value of V, it's a sine wave with a 0 to peak amplitude of V, and if we're interested in the average, the mean value of power, that factor of 2 arrives for that reason. So, much simpler problem to do this one. 330 millivolts squared divided by 2 divided by 39 equals 1.4 milliwatts. And it's watts this time because this is a real active power. Energy is actually leaving the circuit. That was straightforward. Okay, on to number 4. This one's a little bit more difficult. We have a current source here feeding a resistor and a capacitor in parallel. And we're being asked what the reactive power is. Well, we could work out what the total power in the system is, and then the reactive power is the magnitude of the imaginary part of the power. But because this is a resistor, and we know that resistors only give active power, and this is a capacitor, and the capacitors only give reactive power, the only component that we're interested in here is really the power associated with this capacitor. So let's just concentrate on that one. This one's slightly more complicated than the last one because we don't know the voltage across the capacitor or the current through the capacitor. So we can't simply use the formulas S equals magnitude of the voltage divided by 2Z complex conjugate, or magnitude of the current times Z divided by 2, because we don't know either of them. Probably the easiest one to work out is I, the current, because this is a current divider. The current 52 milliamps divides down. Some of it goes through the resistor, some of it goes through the capacitor. And there's a convenient formula for current dividers, which hopefully most of you will have got the hang of by now. That will tell me that the current through the capacitor, I'll call it IC, this one here, is the total current coming in, 52 milliamps, multiplied by the other resistance, the resistance of the other leg, 68 ohms, divided by the sum of the two resistances. So 68 ohms plus the complex impedance of this capacitor. We need to know that. Okay, complex impedance of a capacitor, 1 over j omega c, which is minus j over omega c. Frequency is 500 hertz, so omega being 2 pi times the frequency in hertz, that would just be 1,000 times pi, and the value of capacitance is 10 micro, which is 10 times 10 to the minus 6. So stick that into a calculator and you will get, the answer is about 31.83 times minus j. probably easier if I write it, minus 31.83 J. Right. So down here, 68 minus 31.83 J. That is the current that is flowing down through this capacitor. Now you'll notice that the formula for the power is the amplitude of the current. Don't care about the phase, just the amplitude of the current squared times the complex conjugate of the complex impedance of the component here divided by 2. So I want to know for the power associated with this capacitor, the complex power being dissipated in this capacitor, I'll call that SC, is the current through the capacitor, just the magnitude of that current squared, times the complex impedance of the capacitor divided by 2. What is then the magnitude of this current here? Well, the magnitude of the current will just be the magnitude of 52 milli times 68, 3.536, divided by the magnitude of the denominator here. And again, good old Pythagoras can help with that. 68 squared plus 31.83 squared, that would give me a magnitude of my current of 0.0471 approximately. So stick that up here. SC equals 0.0471 squared divided by 2 times ZC. Well, ZC up here, we've calculated it before, minus 31.83 J. That lot then works out to be minus J 0.0471 squared divided by 2 times 31.83, which is 35.3 times 10 to the minus 3. Or I would write that probably as 35.3 milli. Now, that's the complex power. I'm asked for the reactive power. The reactive power is the magnitude of the imaginary part of the complex power. Well, it's all imaginary. Of course it is. It's a capacitor. It only has reactive power. The magnitude of this complex power is just 35.3, and I'd probably write that as millivar, using the VAR, volts, amps, reactive, to indicate that this is a reactive power and not an active one. And that's what I get for that question. Let's move on.